Okay, I think we are here. Good morning, everyone. I think this is where we left off, talking about the Bohr atom. Can be a little confusing. Quite a number of ideas Bohr is using here. I did suggest a video that just basically goes over the same material as I'm doing, as kind of a reinforcement, or maybe they explain it better than I do. It's very possible. But the basic idea is that Bohr has a traditional, what we think of as a planetary model of the atom. He has has electrons going around in real orbits at real distances from the nucleus, going around at different speeds in circles. And he very much uses the physics of Newton. He uses the equations of Newton's stuff that NASA uses to send rovers to Mars. He uses that same mathematics, that same theory, to produce a theory of the hydrogen atom. He picked the simplest atom, very smart of him, because actually these ideas will not work any further than the very simple hydrogen atom. But by some miracle, it in fact does work, at least to a very good degree. And he knows the energy levels that he wants because he has the Balmer series. He knows what the cascading energies coming down from one orbit to the next should be. He has those series of energies, and Newton's equations will tell him the potential energy and the kinetic energy of his electrons as they circle around the nucleus, just as the planets circle around the sun. He uses exactly the same formula for potential energy based upon the distances, the radiuses. He uses everything the same. The only major difference he has, the fundamental difference, is that he quantizes these orbits. They're not quantized directly by radii. They're not quantized directly by energy. The value that he picks, the quantity, the parameter of the orbit that he picks to quantize fundamentally is something called the angular momentum. The angular momentum is simply the momentum, mass times velocity, times the distance away from the center, from the nucleus, r. So that's the angular momentum in terms of the Newtonian paradigm. And he sets that equal to multiples of h over 2 pi, where h is Planck's constant. This is his, I don't know how exactly he comes up with this, but the angular momentum of these various orbits can only be 1, 2, 3, 4 of those, and you can see it here. N times this unit of angular momentum. And given that one quantization and the rest basically Newtonian physics, he's able to devise this energy scheme. And he posits that as long as the electrons are in these particular quantized orbits, they will be stable. According to electromagnetic theory, they should be radiating their energy away and falling into the nucleus. Bohr says no, as long as they're in these quantized proper orbits, proper distances away from the nucleus, they won't. Why? I don't know, they just don't. This is a premise. This is an assumption. And so with that, he is able to back into all the various spectra of hydrogen. Here is the Balmer series. Here is the visible part that we can see. Here is the Lyman series, much higher, okay, in the ultraviolet. And here is the lower Paschen series in the infrared. And you can see why. The Paschen series is falling from these various energy states only down to 3. So this is not a long fall. So you're not giving up that much energy. And so the wavelengths are long. Here in the Balmer series, you're falling all the way down to the second energy level, long way down. So these are in the visible range. And finally, the Lyman series falls all the way down to what's called the ground state, a very long fall, longest fall possible from these other energy states down to the lowest. And these produce, therefore, much higher energies, shorter wavelengths, This is in the ultraviolet. And he's able to predict these numbers. Well, in a sense, he backs into these numbers with his Newtonian formulas. But what's incredible, what he's able to do is he knows he has to come up with the Riemann formula, the Reichberg formula. Now, the Reichberg formula is traditionally given in wavelengths. Here are the wavelengths that you have to produce to get these, to produce the proper formula, which we know empirically works. Okay, and he's able to derive this formula. That's not the hard part. The hard part, the amazing thing is he's able to deduce from the theory a calculation of what the Reichberg constant should be. This is the driver of the whole thing, right? Here's the energy shell you're falling into. For example, for Balmer, this would be 2, and then M would be 3, 4, 5. You're falling from 3 to 2 to 4 to 2 to 5 to 2, just as you see here, okay? So this part was well known. It's can you actually predict this crazy constant, right? Which is 1.07 times 10 to the 7, it's some crazy number. It's just an arbitrary number in terms of what anybody knew. Bohr is able to derive this number with these set of constants. Reichberg constant is a constant, and it is this, I don't know, nightmare of constants multiplied and divided together. He's able to derive this. This is a wonderful derivation. We do this in high school physics. It takes a whole class to derive this. The algebra never gets beyond, like second, third grade algebra, junior year algebra. It's a wonderful derivation. I chose not to do this. We don't have a whole class to do this. And a lot of you would be glazed over and say, yeah, I take your word for it, Peter. But if you look at these constants, it's the mass of the electron times the charge of the electron to the 4th power divided by 8 over the permittivity of space squared times Planck's constant cubed. You don't make this up. This is derived from his formulas, and this impressed the hell out of everybody over time, little by little. And one person who was very impressed by this was his advisor, his boss, Ernest Rutherford. Rutherford was very encouraging to Bohr, followed his work. When he saw Bohr ran all these ideas by Rutherford, Rutherford was greatly encouraging. And he said, yeah, well, that's definitely begin to publish this. This is impressive stuff. But typical of Rutherford, I have one question here, though. How do the electrons know how to fall from one state to the other? When they're going down, how do they know when to stop to give off just the energies and just the frequencies and therefore just the wavelengths that you want? It seems like they kind of have to know where they're going. How do they know to do that? And there's a very, very profound question, which of course Bohr had no answer for. Okay, it's one that will ultimately be one of the great drivers of modern quantum mechanics, done by Heisenberg and Schrödinger, to answer Rutherford's question. Okay, to finish the story of Bohr's atom, its great success, was we must go back to Moseley, because Moseley is the one using Bohr's atom to show that there's a profound connection between atomic number and the frequency giving out of the characteristic frequency of the X-rays is in fact, something that's inherent in the atom. And what that is depicting the actual positive charge in the nucleus. So I want to complete that story. So we need to go back to the story of X-rays for a moment, because Moseley is using the spectra of X-rays. So it was Max von Laue who finally showed that X-rays truly were a wave nature. Very tough to do. This is something that Röntgen tried initially in his initial experiments, and everyone else tried. Max von Laue, a brilliant physicist, probably the best friend of Einstein. If Einstein had a best friend in the profession, it would be Max. Max realized that if we're going to show that these X-rays, which are very, very high energy and therefore very, very short wavelengths. If we're going to show their wave nature, which you're talking about, everyone knows what we're talking about, diffraction and interference, those are the fingerprints of waves. If you want to show something as a wave, you show diffraction and interference. End of story. If you're going to show diffraction and interference of these very, very short wavelengths, you're going to have a very, very tiny grid of the spectral, grid, the diffraction grading that we talked about. You need those slits to be very, very close together. It was von Lau who realized what would be a natural diffraction grading would be a crystal, because now the openings of the slits would be the opening between the atoms in the crystal. Brilliant idea. He was not a experimentalist. He got a couple of experimentalists on his staff to actually do the experiment, to send X-rays through a crystal and to come out the other side on a fluorescent screen, on a photographic plate, to see what he got. It's very crude. Okay, this very first picture here, up in the upper left here by his picture, it's very crude, but this was recognized as, in fact, not just simply the waves going through in a simple way. These light and dark bands, as crude as they are, was recognized as a diffraction pattern. And over time, these diffraction patterns, looking at this picture over here, in the lower right, became prettier and prettier as techniques grew. It's interesting that von Lau did this work in Munich as a young man. He was 33 at the time, and Röntgen was still the senior professor there. And he was able to go to Röntgen and show him the evidence, something that he was trying to show, ever since in his 40s, to try to show truly what X-rays were. And so it's kind of a nice closure for the old guy. I think he was 67, very close to retirement, that von Lau, under his leadership, he was in charge of the University of the Physics Department, Röntgen. This was done kind of on his watch by one of his brilliant faculty members, von Lau. It's kind of a nice story. Who took this and turned this into a real science is this team here, a father and son team of William Bragg, both William. And they turned this into a real science. They turned this away from proving over and over again that X-rays were a wave and using the diffraction patterns coming from the X-rays to study the crystals. And we have the whole new science of crystallography, of X-ray crystallography. And they're the ones who perfected this, who developed the mathematics of how to analyze pictures like this, to have this picture come back to what the structure of the crystal must be, if that's the diffraction pattern. They're the ones who did this original research, and it has only gone on from there, becoming more and more important. And probably the most famous example would be Rosalind Franklin's diffraction pictures of the DNA crystal. Remember when we were talking about Madame Curie? I couldn't remember the second woman when they give the survey and they give you lists of names. Who is the most famous, a woman scientist? And Curie always wins. And I was trying to remember the second name who comes in second in these polls, and I couldn't bring her name back. Rosalind Franklin. Well-known story that's told, in Crick and Watson's The Double Helix. She was very instrumental. She was the one who did the diffraction grading. She's the physicist who knew the technique of how to do this. She's the one who gave the analysis of what they were looking at, and it was Crick and Watson realized, okay, with that analysis, if you're talking about a helix, then they go back to the biophysics to come up with the actual structure of the DNA molecule. But nothing happens without Rosalind Franklin's work. And it's been often said that she really deserved a third, part of the Nobel Prize that they won. And I think even eventually one of the two of them finally agreed in their older age that, yeah, she really did not get the credit that she deserved. But anyway, the story of X-ray crystallography probably has its single most famous incident here in the analysis of the DNA molecule. So now we can complete the Moseley story. Moseley now knows of Bragg's work and how to analyze these diffraction um, patterns coming from the X-rays. So remember what he's doing. He's taking a Crookes tube. Yeah, he's taking an old cathode ray tube, and he's shooting cathode rays, electrons, against a heavy metal, which is producing the X-ray beam. And he's able to take the spectra of that. How? By sending it through a crystal diffraction grating, the way the Braggs are doing. And he develops the technique, learns the technique, and learns how to read the spectra, the diffraction grating picture, to produce a spectra. What he's interested in is this sharp spike. He's interested in the so-called characteristic X-ray. Okay. So he becomes a master at discerning from the diffraction patterns this spike. And he finds, right, this so-called Moseley's law. He finds that the square root of the frequency of this spike has a linear relationship with the atomic number. Remember, the atomic number is simply the ordered list. The periodic table is laid out by atomic mass and chemical properties. And when you have that all laid out, you simply start numbering them. Well, this is 1, 2, 3, 4. He finds this fundamental relationship between the characteristic frequency of the element and that atomic number. He knows that this atomic number is something fundamental to the atom. What is it? Okay. Here's another very famous picture done by Moseley. Here we have decreasing frequencies, and the heavy lines here are the characteristic frequency. These are all spectra. And this is the characteristic frequency of cobalt and the characteristic frequency of iron. And here the elements are actually getting lighter and lighter. We're going from copper down to calcium. So we're going down in atomic number, and therefore we're going down in frequency. And this with the square root gives you that linear relationship. Okay. And so this is Moseley's law. Moseley's law says that the square root of the frequency is proportional to the atomic number. You turn proportion into an equation by having a constant of proportionality. So this is Moseley's law. Notice if you were to square both sides of Moseley's law, you would get an equivalent mathematical statement that the frequency is proportional to the atomic number squared. I'm simply squaring both sides. The frequency is proportional to the atomic number squared. He has a conversation with Bohr. They both work for Rutherford in the lab. Moseley is 26, Bohr is 28. They're both virtually unknowns. And Moseley tells Bohr about his research and about what he finds and this law. Bohr is basically through his model of the atom that we've just gone over, and he realizes that there's a profound connection here. And it's this. What's happening? The electron is being smashed into the heavy iron or whatever material he's using here, the various different heavy elements. So an electron is sent in and knocks away the inner electron, and the projectile electron goes on its merry way. And what happens is when this electron is knocked away, it leaves a hole. And when the electron knocked away is down at the lowest energy level, when the electron that penetrates into the atom of copper or iron or nickel, when it knocks away a deep electron inside, an electron from the outer shells can fall all the way down. Tremendous drop. And according to Bohr's model, that will release a very high energy frequency. And that's the characteristic frequency. It was a very nice mesh of what Moseley saw and the explanation of Bohr's model. But here's the kicker. Bohr was able to show using his model, so the high energy electron from the outer orbit falls down into the lower empty, giving off that spike, that very high, that very bright first of all, and very characteristic frequency. It's brighter than any other frequency around it. Okay, so it's a tremendous intensity of this frequency. What's causing this thing is this process here of the electron coming in, hitting the metal, the cathode ray electron coming in and knocking out the electron inside the atom, and then an outer electron in that atom falls down, and in the process, as we know, gives off a certain frequency. Bohr is able to show in his model that that frequency is proportional to the central positive charge of the nucleus. Remember, his model is based upon basically these Newtonian type equations, where the central nucleus is like the sun, and the sun has its, very much controls the orbits, okay? And controls the energy levels that the planets are in. And so it's not at all surprising that when you come to Bohr's model and you want to know what the energy difference is as you fall from a high one to a low one, it's going to involve the sun. It's going to involve the mass of the sun. It's going to involve the charge here, and instead of mass, we now have charge, the mass of the positive nucleus. And Bohr is able to show that the frequency is proportional to the positive charge in the nucleus squared. It's exactly the same equation. And so, in fact, the positive charge of the nucleus is the atomic number, and that's what closes the gap. Okay, the wonderful collaboration between Moseley and Bohr. As short as it was, it didn't take Bohr long to see the importance. And in fact, Moseley as well. Moseley was aware of Bohr's work. They were friends. And when he saw this relationship, he had a hunch that, this was something that Bohr could use. The other great, and I'll stop for questions just after this. The other great confirmation of the Bohr atom was this very famous experiment by Frank and Hertz. You recognize the name Hertz. This is Heinrich Hertz's nephew. And they took a Crookes tube, a vacuum tube, a cathode ray tube. Yeah, they keep using this tube over and over and over again. How many experiments have we seen using the cathode ray tube? Anyway, they fill the cathode ray tube with mercury vapor. Okay, evacuate it out as best they can and have a little bit of mercury vapor in here, heat it up. And they have their filament, they have their cathode shooting out electrons. Used to be called cathode rays. We now know that they're electrons. And they shoot it towards a positive grid. And so therefore the electrons are accelerated across, going from the negative to where they're attracted to the positive. And once they get through this grid, they then have a little bit of an uphill. They create a little bit of a negative voltage here with the negative plate. So they want to make sure that the electrons that reach the grid being accelerated here, the acceleration will stop once they get to the positive grid. As they get through, they want to make sure that the electrons have enough energy to hit the collector plate, which would register as a current. What was their idea? What are they after? Well, they want to know if the electrons are being, in any way, the energy of the electrons are being affected by interacting with the mercury atoms. That was their question. As the electrons came across, going through the vapor, how would they lose energy by interacting with the mercury atoms? Certainly many electrons wouldn't touch the mercury atoms at all, and they would go right through, and they would have exactly the energy that you would expect. When you send an electron through 5 volts, the electron will have 5 electron volts of energy, and they know they'll calibrate it so that'll be enough, more than enough to get to the collector plate, and they'll be able to know exactly what current they should be expecting. But some of the electrons will interact with the mercury vapor. They will lose some of their energy to the mercury vapor. They were interested in what would happen there. Doesn't sound like it has anything to do with Bohr's atom, does it? It didn't. They admitted afterwards they weren't even aware of Bohr's model of the atom. Bohr's model of the atom was not all that important to anybody. It took a while for people to even learn about this. And this experiment was done at the same time that Bohr was producing his papers, basically only discussing them with people like Moseley and Rutherford. And this is the very famous graph that they produced. Okay, this is one of the most famous graphs in the history of physics. Okay, what is going on here? Okay, what we have is voltage down the bottom, and we have the amount of electric current that's hitting the collector plate. And this is a proxy for the energy of the electrons that are able to get through the grid and hit the plate. So this electric current here is a proxy for what is the energy of the electrons. And as you pick up the voltage from 0 up to 4.9, the amount of electrons hitting the collector plate gets larger and larger, which is not surprising. Okay, the energy is getting higher and higher, and they're able to, get through the grid, seem to be totally unmolested at all by the mercury, having totally oblivious of the mercury. The current is rising, the energy of the electrons are rising as if we were dealing with a pure vacuum. And all of a sudden, the bottom drops out at 4.9 volts. At a voltage of 4.9, and therefore the electrons have an energy when they get to this plate, they would have an energy of 4.9 electron volts. The energy is sucked out of them. The energy has been sucked out of them, and the current in the collector plate collapses. Sure, some electrons are getting through, they're not touching the mercury at all, okay? That's why it doesn't fall all the way down to 0. But after the 4.9, the current begins to recover. And now let's say here we're at 8 volts. What's going on at 8 volts? Well, at 8 volts, we've passed that first peak. So there's a lot of electrons getting through, unmolested by the mercury, and they're easily getting through the grid and hitting the collector plate. And the current is growing. The amount of electrons that have this energy, it's getting larger and larger. And at exactly twice 4.9, the bottom falls out again. The current collapses. At a voltage of 9.8, the energy again of many, many electrons are just being sucked away, and they don't have enough energy to get to the collector plate. They can't get up that hill. And it happens again at 3 times 4.9. What the heck is going on? They did not expect this. Okay, they expected some kind of a graph, but this kind of regularity really surprised them. And again, when Bohr heard about this, Bohr was able to say, "Hey, you've just corroborated my theory." What's going on is if you take that 4.9 electron volts and put it through Planck's equation, you'll find that the frequency of light would be 2.54 nanometers. That's in the ultraviolet range. What I'm telling you, what's happening is the electrons that are interacting with the mercury vapor is these electrons are hitting the mercury atom. They're hitting an electron in the mercury atom. They're being absorbed. Their energy is being totally absorbed by the electron in the mercury atom. They have no more energy at all. They're not going anywhere, okay? Because this is happening very, very, close to the mesh. So there's not enough energy to get to the plate. And therefore, what you should see, and what they did see, is you should see light being given off at 2.54 nanometers. You should be able to see ultraviolet light at that wavelength. I say see, detect. And that's what's going on. That at that energy, that's just the energy that the mercury is looking for to absorb the electron. Before that, it has no interest in those energies. Those energies are not something that the mercury can deal with because it's not an energy that's between, none of those energies are between any two energy levels. But this energy of 4.9 exactly will take an electron in the mercury atom from one energy level up to another one. That one it likes, that one it'll absorb. And then as you pick up the voltage and the energy of the electrons gets higher and higher. Okay. What happens when the bottom drops out again? This is the amazing part. At 9.8 volts, well, halfway through the actual distance, literally the electrons gain energy by distance going through the voltage. At halfway through, the electrons will have 4.9 electron volts. Many of those electrons will meet a mercury vapor right here. The energy will be sucked out of them. We'll get the ultraviolet light being given off. There's enough distance between the middle to the grid to pick up another 4.9 electron volts, because the total voltage it's going through is 9.8. It'll meet the grid at this 9.8. It'll have another 4.9 electron volts of energy. It'll be sucked out by the mercury vapor that's hanging around the grid. It'll happen all over again. And therefore, Bohr says, when you see the light coming from the, there'll be ultraviolet light coming out of this tube, right? There's energy being released by the mercury atoms. What you'll see is not just the normal spectra of mercury, which was well known. What you'll see here is that ultraviolet wavelength of 2.54 is being given out twice in this case, being given out 3 times in this case. You should find not only a ultraviolet light line of 2.54, but it should be much, much brighter than the normal everyday spectra of mercury. This is Bohr's prediction, and this is exactly what they found. Here's the 2.54 in the ultraviolet range. This is the full mercury spectrum. Okay? This is what it would look like normally. The 2.54 is not nearly the brightest line. There are much, much brighter lines. Okay? These here are lines in the red. These are lines here, and you can see the colors behind us. Here, here are all the ultraviolet lines. So this 2.54 line is certainly there. It's there in spades. And in fact, in the spectra of this experiment, it was by far the brightest line. It's exactly as Bohr described it. I'm sorry for the long, it's a long explanation. It's not all that simple to see. And I want to stop here and take questions. But this was quite amazing that the experimenters were looking for something in a simple kind of way, and they, in a sense, stumble across very strong support of the Bohr model. And of course, Bohr was just delighted with this. And it is a very, very famous experiment because of what it did. It really put the Bohr model on the map, because what all physicists like is they like experimental data. And sure, Bohr was working from experimental data. He was working from old data. He was working from those spectra of the Balmer series. Those were all in the can. He could work from those. This was a new experiment, which was done even without the knowledge of the Bohr model, and it goes ahead and supports it. It's impressive when that happens. Okay, are there any questions do we have so far?
Peter, we have 2 questions and a comment from Joe Parisi. At the time of Bohr, etc., what was the explanation of why the innermost electrons did not collapse into the nucleus?
Bohr just postulated that there are these definite quantized orbits that will be stable. Why Bohr? Well, they have to be, right? Or we wouldn't exist. There would be no atoms. There'd be no us. So there must be, if these electrons are not in the nucleus, okay, we've established that there are electrons that are in the atom that are not in the nucleus. Okay, they can't be stationary. We know that. If they were stationary, they certainly would be sucked into the nucleus. So they have to be going around. They must be moving. Okay, just the way the planets aren't sucked into the sun. Okay, if you were to stop the Earth in its tracks, in its orbit, it would immediately start to gravitate towards and fall into the sun. What's keeping the Earth away from the sun is the fact that it's moving around it. We don't have time to explain all of that in Newtonian physics, but that's essentially what's going on. Bohr used the same paradigm. that the electrons must be moving. They couldn't possibly be stationary. Well, once they're moving in a circle, because they're electrons, because of Maxwell's theory, they're going to be giving off energy. Therefore, they would also be falling into the nucleus because they don't have the energy to sustain themselves out at that potential energy level. We know that's not happening. Clearly, that's not happening. Atoms exist. So therefore, I just postulate that there must be these stable orbits. It's really as simple as that. He had no explanation for it. He says, you know, it must be so, right? I don't know why. Which is done, of course, all the time in science. Okay, we can take Newton's law of gravity. We can write down Newton's law of gravity. G times this, multiply the two masses divided by the distance squared. When you asked Newton, and he was asked, "What is gravity?" He said, "I don't know. But if you want to know what the force is between two objects, that's the formula. I have no idea why two objects will attract each other because of their mass, but that's the formula to use to calculate the force." When Einstein postulated that mass warps space and time to produce the illusion of the force of gravity, and he was asked why, he said, "I have no idea. I have no idea what mass is doing to warp space and time, but here are my formulas to show you what that warping is." So this is not surprising that you make a fundamental assumption that, you know, you build a theory from, and that's what Bohr was doing. Next question.
Carol Reller asks, didn't part of Moseley's work result in slightly rearranging the periodic table by atomic number rather than atomic mass as originally laid out by Mendeleev?
Remember now, he did not rearrange the table at all. The table was laid out perfectly fine. He just gave the understanding finally of what those ordered numbers were. He still, the periodic table still has a couple of switches, I think famously argon and potassium. If you have a periodic table, I think the argon is slightly lighter than the potassium. The argon is at one end, and then you go start the next column, next row down below. So they're still the way they are. There's still a couple of places where you go from a heavier element down to a slightly lighter one. No one's changing that. Moseley was not changing that. But he showed what these ordered numbers were. Interestingly, he was able to show that there were 4 elements not yet discovered. Just 4, because that was still a question, particularly down those, you know, those elements down the bottom that we never know what the heck they are. He was able to show that there were exactly 4 elements missing from the scheme, and the search was on to find those. Anything else?
Okay, we have a comment and one more question. Bridget Hansel says, UV sterilizers used today to sterilize water, etc., use this principle.
I'm sorry, using sterilizers with water, I didn't hear the end.
UV sterilizers used today to sterilize water, etc., use this principle. And
I'm sorry, what principle?
And it's Bridget hasn't supplied that information.
Okay.
So maybe
well, let's take it up at the end of class. Is there anything else?
Yes, Nancy Chamberlain asks, why does Bohr posit that the electron that falls into that vacated inner orbit is from the outermost orbit rather than from the orbit right next to the vacated one?
No, well, that's a very good question. He wasn't saying that. He was saying that those were not the predominant one. There was certainly electrons falling from all different places down to the lowest one. But he was saying that the most of them were coming from the high place. Why? Because they're more unstable. They're more looking to get to a lower energy level. There's kind of a hokey, complicated kind of explanation. So it's not that all of them fall from the high place. It's just that most of them will fall from the high place, and that's why that particular line will be the brightest of the lines. If you could really see some of the really, really dim lines, you would see other lines. But this line falling from the very high to the low is brighter than all the rest, and that's that characteristic frequency that we see so so starkly in the spectra, in the X-ray spectrum.
That's it.
Okay, should I continue, Brett?
Yes.
I will continue. Okay, so so Bohr's atom was very successful for hydrogen, but not, yeah. When you looked at hydrogen spectra very closely, really inspected in this minute detail, subjected to a magnetic field, a strong magnetic field, little lines began to pop up in the spectra, lines very close to the regular the four major lines that we all know. Tiny little lines were kind of around them, and that had no explanation. Also, the spectra of all the other elements had no explanation. The person who stepped in to try to help was the great theorist Arnold Sommerfeld, who we'll hear more about when we get to regular quantum theory, modern quantum theory. Staying with the Newtonian paradigm, he says, well, Bohr, why don't we expand here from these circles? Just as Galileo and Copernicus were hung up on the circles, why don't we take a page out of Kepler's book and let's go to ellipses? That'll give us a lot more degrees of freedom. We can have a lot more energy levels, minute energy levels in, sharing the same overall big energy level. If they're all, just having different kinds of orientations of the ellipses. And so here would be a picture of, for example, the fluorine atom. If you count the number of ellipses here in circles, there's two circles, a little circle and a big circle, and then there are three small ellipses and four larger ellipses. You have 7 paths for the 9 paths for the electron altogether, and we know that the atomic number of 9 is fluorine. So this would be Sommerfeld's picture of the fluorine atom, very ambitious to try to come up with the spectra of fluorine. That's the whole game, is to try to predict the spectra of fluorine from these different energy levels that he could produce using the Newtonian equations like Bohr did with, of course, the quantization. Not very successful. Okay, it was a good try. But what Sommerfeld did do was, in looking at the ellipse as an orbit, we know that a circle takes just one number to describe the orbit, the radius. For an ellipse, it takes 2. You need to have the kind of the length of the ellipse and the width of the ellipse, right? You need both, the red line and the blue line. Traditionally, half those values are called A and B in analytic geometry. Now that Sommerfeld had 2 numbers to deal with, that he could use, not just one, he could develop a whole series of what he called subshells inside the overall shell. When A and B were equal to each other, you'd get a circle. When A was twice as big as B, you would get one kind of an orbit. When A was 3 times as big as B, you would get a longer, more flattened kind of an ellipse, all with the same kind of energy level. So here, what he was essentially quantizing was using as a quantized variable that angular momentum, the orbital angular momentum. These various different ellipses of different shapes had different angular momentums. Same energy, they all were in the same kind of energy shell, but they had different angular momentums based upon that quantization. So it gave the Bohr model more elbow room to have different and slightly different kind of energy levels, which could produce those slightly different spectral lines. The lines weren't quite falling as far, or weren't falling a little bit further, and therefore giving off slightly different wavelengths as they fell from one orbit to the other. Sommerfeld's elliptical orbits gave you that ability to do that. You can imagine the math here got very, very complicated very, very quickly, and it really collapsed under its own weight. But what the legacy that came out of this, though, was we have, besides Bohr's essential energy level, which came to be called the first quantum number, n being 1, 2, 3, 4, 5. Sommerfeld introduces a second and even eventually a third quantum number. The second quantum number would be this value that quantizes the angular momentum, the orbital angular momentum, to give the different shapes of the orbits. So he introduces a second quantum number. He then orientates these, because these are, after all, three-dimensional. These are ellipsoids. They're not really ellipses, right? Yeah, like a tube, like a blimp, like the Goodyear blimp. These are three-dimensional objects, and not only do they have a different shape in terms of how long and wide they are, but how they're orientated in space. And that also gets quantized by Sommerfeld. Sommerfeld is not one of the greatest theoretical mathematical physicists of his generation for nothing to handle this kind of modeling, to do this. So he actually introduces a third quantum number. And these numbers actually wind up staying, not under the guise exactly as Sommerfeld envisioned them, but they actually do show up in the Heisenberg and the Schrodinger quantum mechanics, which we will get to. So this was kind of the last dash of trying to have this physical model of Bohr, to extend it to a more intricate kinds of physical orbits. These were literally physical orbits in space of electrons, trying to work with some kind of a Newtonian paradigm, but using the quantization of certain elements of the orbits, like energy, like angular momentum. Okay. So I expanded this presentation. I wanted to actually finish up the era of the Bohr model. What was going on until 1924, when all hell breaks loose and the new quantum theory arises? Well, a number of important things did happen under the, during the time when the Bohr model was the best model, was well known during those years, and kind of things were developed under the, under the auspices of this working model of the atom. So let me go through those. Remember in 1903, Madame Curie was able to show that radioactivity, in fact, was an atomic property. Had nothing to do with how the atom was, in some kind of a compound. Didn't matter. Radioactivity was not affected. Didn't matter how hot it was, how cold it was. If it was in a melted state, if it was in a vapor state. It was not a property of the chemical situation of the atom. It had to do with just the atom itself. Bohr was able to go further with his model, using his model now for trying to make deductions from his model. He was able to show that, in fact, radioactivity was, in fact, a nuclear property. Certainly alpha particles were there. They were, after all, helium nuclei. They certainly couldn't come from, the electrons buzzing around. He was able to show that beta particles and the gamma rays, in fact, were nuclear processes. Very easy. Although the beta particles are electrons, he could show, because he knew the energy levels of the planetary electrons, that there's no way that those measly little energy levels that he was using to give off the spectra could in any way compete with the tremendous energy coming out of the beta electrons. The beta electrons were a totally different class, okay? And therefore they were coming from a fundamentally different process. It had nothing to do, beta decay had nothing to do with the planetary electrons falling from one state to another or being shot out, from one state to another. No, this was a different level of energy. We're dealing now with, somehow or other, electrons inside the nucleus being shot out in beta decay. And gamma rays were even easier. The gamma rays, of course, are beyond any energy that the electrons could possibly muster. Right? The biggest frequencies we saw, were those of Moseley, which, were the X-rays. It wasn't even getting close to the gamma ray range. So the planetary electrons had no apparent ability to give off that kind of energy in the gamma ray range. So the only other place to look, if you're going to look in the atom, if it isn't going to be in the planetary electrons, it's going to have to be in the nucleus. Okay, we come back to Rutherford. Rutherford proposes this really simple kind of idea, when you think about it. What is the nucleus made of? Well, we know the nucleus has this positive charge. Let's take a beryllium atom. Okay, a beryllium atom has atomic number 4. We now know it has a positive charge of 4. So it's got 4 positive charges, is what Rutherford wants to propose. Just as the electron is the fundamental negative charge, he posits what he calls at the time a positive electron. And there will be 4 loose positive electrons in the nucleus giving the positive charge. But where does the atomic weight of 9 come from? The atomic weight of 9 comes from 5 more positive electrons being hooked up, married to regular electrons, and they would be neutral, right? We know the electron has virtually no mass, okay, so there's no problem there. But what they do is they neutralize the 5 other positive electrons, and now you have a total weight of 9, but a charge of 4. Not particularly profound, but has some merit to it. And one of the things that it explains is it explains beta decay very nicely, because one of these nuclear electrons, some mechanism of radioactivity, is throwing this thing out, throwing this outside of the atom. And what happens? Well, once this marriage is broken and this electron is gone, this positive electron now becomes a free positive electron, and the charge on the atom goes from 4 to 5. We have beta decay. We have a transmutation from beryllium up to the next element. Try to forget what it is. Element 5. What is element? Nitrogen, I think. Okay, so let's take a look at a real beta decay. Let's have radium decay into actinium. Okay, well-known reaction. Okay, what happens is radium with 88 now, a charge, positive charge in nucleus of 88, goes to 89 because it loses an electron, loses the beta particle, which is the electron. Notice the mass stays the same, 28 to 28. Okay, it's a very nice balanced equation. 28 is equal to 28 plus 0. And as far as the charge in the nucleus, 88 equals 89 minus 1. Okay, so this is Bohr's explanation of beta decay. It's very nice. It's worth. It's kind of simplistic, but it does explain this idea. Well, he becomes unhappy with this idea and posits something else. During the war, when all of his senior boys had gone doing war work, and Rutherford did some war work. He did some work on sonar, but he stayed in Cambridge and wasn't running around the field or anything. And he mostly was by himself with just younger people. Most young men, right, were gone to the war, even the undergraduates. So he was pretty quiet there. And he did this experiment pretty much by himself, which is very low-level assistance. He took nitrogen. First of all, he started with just air, which we know is mostly nitrogen, right? 80% nitrogen, 20% oxygen, basically, more or less. And he fired alpha particles through a Crookes tube. Yeah, of course, what else? Cathode ray tube type vacuum tube. But instead of using electrons, he used alpha particles, set up a radium source, let them naturally shoot through the air. And he noticed that these high-speed positive charges were being produced. He saw how they were collecting, a positive plate. The alpha particles were somehow or other creating these high-speed, single individual positive charges. Rutherford, being the genius that he is, he said, maybe something's going on with the nitrogen or the oxygen. Why don't I simplify this? Let's just take pure nitrogen and then take pure oxygen. So he takes pure nitrogen in his glass, does the same experiment, and what he discovers is not only are these high-speed positive individual one positive charge particles being knocked out, but oxygen is developing in his tube. Oxygen is just being made out of nothing because he's starting with pure nitrogen, and he's only shooting through helium nuclei, and all of a sudden he has oxygen and these high-speed positive charges, individual single positive charge. And this is the equation he writes down. Not on day one, it takes a while. But again, if you look at this balanced nuclear formula, the nitrogen is being knocked by the alpha particle, by the helium. The nitrogen is being transformed into oxygen. This is the first time an element is being artificially transformed by a human being in the lab. And what's left after the oxygen is created is this high-speed particle which is being shot out, the one charge, one positive charge. And again, if you look at their masses, 14.4 is 18, and 17.1 plus 1 is 18, and 7 plus 2 is 9, and 8 plus 1 is 9. Here we have a balanced nuclear equation. And what Rutherford simply posits is that, first of all, this nitrogen is being transmuted into oxygen just the way radium is transmuted into actinium, just as uranium is being transmuted into thorium. He's doing this artificially by banging the nitrogen atoms by the alpha particles. He's doing exactly the same process. And what he's giving, what he's knocking out of the nitrogen, what he's freeing up from this interaction is a piece of the atom. And just as J.J. Thomson said, the original electron was a piece of all atoms. It was the fundamental negative piece. Rutherford says what's being knocked out is the fundamental positive piece of all atoms. Now, this was a speculation that was around for years, that hydrogen was, in fact, the lightest element, and that all elements were made up of some kind of combination of hydrogen atoms in some way. But here's the experimental proof. He's producing hydrogen nuclei, okay, and gives it the name proton. And so this is the discovery of the proton. You're wondering when we could start talking about protons? Well, Rutherford allows us to begin talking about protons. And it's a wonderful story. He doesn't actually publish this until 1919 when all the boys come back, and he does the experiment again with the boys, senior guys, make sure he's got it right. But this is really the last of his great individual discoveries of Rutherford. He is the discoverer. Long time speculated by many, many people. Yes, he is the discoverer of the experimental evidence of the proton. Soon after that, he goes back and looking at his nucleus, and he no longer has, he's skeptical of these protons and electrons being married together. He doesn't see that as too much of a stable situation. And he does the first speculation, and this is a first. He's the first one to speculate that maybe, maybe these marriages of these positive electrons, now called protons, and electrons being married together inside the nucleus is really not such a good idea. I don't see this as a very stable configuration at all. In fact, I think what's really going on is that thing is actually its own particle, which he calls a neutron. And it takes until 1932 for one of his boys, Chadwick, in the Cavendish laboratory, under Rutherford, discovers the neutron. Okay, that's a story I hope we'll get to before the course is over. Okay, so this is just Rutherford's scientific legacy. You can see just how impressive it is. And if you go further, after the end, I've put a few more slides at the back about Rutherford's life and his, the students that he had and his career and stuff. I think it's worth just to read through. Interested in this, certainly one of the great scientists of the 20th century. Okay, speaking of one of the great scientists of the 20th century, we now turn to the work of Einstein. Einstein, of course, was a pioneer in quantum theory with the explanation of the photoelectric effect. His last great real contribution in terms of adding to the theory is here in 1916. After he finishes publishing the relativity, theory of relativity, he turns back to quantum theory. And he develops the idea of these quanta, these individual quanta. I think by 1920, we can call them photons. Let's call them photons so we know what we're talking about. That these photons have momentum. And his argument is very simple. The algebra here is very simple. From special relativity, here's the formula for what energy is. It's actually a Pythagorean kind of a sum. The energy of a particle squared is actually the momentum times the speed of light squared plus the famous mc squared, the so-called rest mass squared. And this is a very famous formula coming out of the theory of relativity. The total energy squared is equal to the energy of its motion as depicted in its momentum plus its rest energy when it's not moving at all, mc squared. Okay. Well, for a photon has no mass, right? So therefore, it only has this PC component. So the energy is equal to the momentum times the speed of light. If, you know, and certainly electromagnetic theory does posit that light does have a pressure, can exert a pressure. This is in the classical theory. So this is also substantiated both by his theory, special relativity, and classical theory. And so we have for light, and photons, of course, are light, that the energy is equal to the momentum times c. Well, he takes the other two fundamental formulas. He takes Planck's formula again, that he worked so well in the explanation of the photoelectric effect, that energy is equal to h times the frequency, and the frequency times the wavelength is equal to the speed of light. Fundamental connection between frequency and wavelength of any electromagnetic wave. So follow the algebra here. Taking this equation up here, P is equal to E over C, but E is equal to HF according to Planck's formula. But what is F over C? What is F over C? Well, come over here. F over C is 1 over lambda, right? F over C is 1 over lambda. So F over C is lambda down the bottom. So the momentum of a photon, according to Einstein, would be h over its wavelength. This will become a very important formula for us. Now, what Einstein is saying is that these photons have momentum that are associated directly with their frequency, or in the simplest way to write it, their wavelength. This is a little bit hard to follow because, again, you know, his photon theory is not accepted by everyone, by no means. But he puts this thing forth, that now individual photons have momentum, like particles, and they're measured in this way, Planck's constant over the wavelength of the photon. I know it's crazy to even speak of a particle having a wavelength, but there we have it. You're in the middle of quantum theory. What can I tell you? Just to remind you of how still skeptical people were about this idea of particle photons, we have Planck in 1918 making the following statement. In fact, the question whether light rays themselves are quantized, or whether the quantum effects only occur in matter, like my black body radiation, he's still trying to say, well, you know, it only really happens in black body. No, the question is, do light rays themselves are quantized as photons, or whether they're just an effect, like we see in my black body radiation formula, is the first and most serious dilemma confronting the entire quantum theory. According to Planck, the existence of photons was still. This is why you have Millikan's so important data that we looked at last time to show that the photoelectric effect was described exactly as Einstein predicted those energy equations to be. And we saw in his quote in 1916 that he was skeptical. In 1918, Planck is still skeptical. This is very, very hard for physicists trained in the classical tradition to get their minds around this idea of light comes in bullets. Very, very difficult to accept this idea. What wins the day is this experiment here called the Compton Effect, done by Arthur Compton, who goes, American physicist, becomes very, very important in the Manhattan Project. He's Enrico Fermi's boss, over in charge of the whole development of all the reactors. Goes on to be in charge of the great reactors in Washington and in Tennessee. He and Millikan are kind of like the two major, and I guess, what's his name from the cyclotron? Who am I thinking of? Oh, another senior moment. Anyway, these are like the senior guys, you know, when they come to build the bomb and put together the senior team who's going to run the whole thing. Compton is one of those very, very few. But here in 1922, he does the following experiment. He starts with a very high energy photon, okay, an X-ray photon, and smashes it into cold carbon atoms. And so therefore, the energy compared to the X-ray is very, very low. We can virtually say it's at rest. And so he uses an incoming frequency called f sub I, okay, of the photon, of the X-ray. And what it does is, the word is it scatters that X-ray and it knocks an electron out of the carbon atom and sends it flying. He's able to record these. He's able to measure, of course, his X-rays coming in. He's able to see his scattered X-ray coming out, and he's able to measure in the cloud chamber his electron being knocked out. He notices that the frequency of the scattered electron is lower than the frequency he uses coming in. Well, not surprising. Some of that energy goes to the electron. And we're not surprised that he verifies the conservation of energy. Okay? This is not surprising. The photoelectric effect shows the same thing, okay? That the energy coming in, the original photon of the X-ray, the energy is divided between the scattered energy of the scattered photon plus the kinetic energy of the knocked out electron. Fine. But we know that each frequency has associated with it a wavelength, because the frequency times the wavelength equals the speed of light. He's able to calculate that wavelength from the known frequencies that he measures. And what he's able to show is that Einstein's momentum equation holds in this process, that the momentum of the incoming X-ray photon is equal to the momentum of the scattered photon plus the God's regular, normal, everyday momentum of the electron. Okay? And what really gets physicists going is that this V is a vector quantity. Not only do you have to get the number right, but you have to get the direction right in order for the conservation of momentum to hold. V not only has to have the right value as these two lambdas, it also has to have the right direction. And the direction of the scattered photon has to have the right direction, so that if you notice, the momentum of the incoming photon, if it truly has one, is only in the x direction, so that the y amount of momentum in this direction better cancel out the y amount of momentum in this direction, and so that we only have an x component of momentum in the original direction. The directions have to be gotten right, and his formula and his measurements show that. This is very impressive. And again, physicists like to see the data. He's able to show not only the conservation of energy, which is kind of old hat, he's able to show the conservation of momentum. Classical physics guys only particles really have momentum. Only the momentum of particles can interact with the momentum of other particles. We now have X-ray photons interacting with the momentum of an electron. These are particles. They act like particles. They follow the laws of particles. And so it is the Compton effect which really helps solidifies Einstein's notion of the photon. So a very famous, very famous experiment. Okay, I would be remiss talking about this era of the Bohr atom, not to mention that relativity was also published during this time, and 1919 is the famous Eclipse Experiment, where you see the warping of space by seeing that the star coming near the rim of the sun was out of alignment. With the eclipse, sky was dark, and you could see where the star looked like, as opposed to where we knew it was, and in fact it was in the wrong place. This is something that was well known. Refraction will do the same thing. A star coming in low on the horizon in the evening or in the morning is out of place. This was known to the ancient Greeks. Ptolemy made all these adjustments in his catalog. But this is not done by the refraction of the thicker air. This is literally done, according to Einstein, by the warping of space-time. And here's the famous picture, taking the picture of the stars. Here's where the star is in the sky without the sun there. And this is taken during the eclipse, where it is moved. It is visually in a different place because the light has been bent. So I would be remiss to talk about this era without mentioning that. Okay? And while we're on the subject of Einstein, let's talk about one of the great technologies coming out of the photoelectric effect, which is the photomultiplier. Okay? All astronomy would be nowhere today, literally nowhere, without the photomultiplier. And its applications are, in fact, everywhere. It was the original electric eye, where if a beam of light was going through, the electrons, photoelectrons, would be given off, and a little current would be created. And the engineers would devise a circuit that if the light was broken and that little current would stop, well, then the big wheels would turn to do something else. Open a door, turn on the lights, wash the windows, whatever. Okay, so that was like one of the very original ideas. But the idea to take a photon of one, starting off with as little as one photon, the dimmest possible light you could think of, subjected to the photoelectric effect to give off an electron. Now we have an electron. We can use the process of secondary emission to cascade, having one electron produce two, and having two produce four, not four, but in fact 40. And although these two electrons here would have only the same energy as this one electron here, you can't make energy. But there's a great voltage between these two dinodes. So as they move, as these two electrons of half the energy of this original guy, as they move from here to here, they will pick up energy because of the actual photomultiplier tube, because of the voltage that's being crossed. So that these electrons are not only multiplying, but their energy is staying very high. By the time we get to the collector anode, we have a tremendous current, and that current is nothing more than a reflection of the number of photons. Okay? We've magnified the light. By the way, secondary emission was first found by our friend Paul Villard in 1899. Remember the guy who first discovered the gamma rays? He was the first one to see this. Remember, the photoelectric effect was well known in 1899. Okay? It was actually discovered amazingly by Hertz. Interesting irony. The guy who was creating the experiment to show that you could make an electromagnetic wave was the first one to notice the photoelectric effect, which Einstein showed 20 years later that light, in fact, was not a wave. Makes your head spin. Okay, I guess we'll have to stop there and open up the mic. First of all, Greg, do we have any questions from the chat?
Yes, we got a couple questions from the chat. Joseph Staples asks, when an electron in the outer shell falls to an inner shell, does that change the valence of the atom?
Well, yeah, we haven't talked about valence, and we will, because when we get to trying to understand the periodic table, we'll talk about the valence electrons. But certainly remember, the valence electrons are the outside electrons. So if you're losing outside electrons to go inside, that will, by definition, change the valence. If in fact there's not some others, yes. So the shorter answer is yes. Let me leave it there.
And last question from Timothy. This is regarding the Feynman lecture. What was the, quote, ignorance of Feynman at the end of his lecture? Was it the statement that there is probability in the fundamental laws of nature?
Well, certainly that was one of his, messages, that nature on some level, as he would call the quantum level, right, is inherently probabilistic in that sense. So yes, that would be a fair summary of one of the major points that he's trying to make.
And
Okay,
that's it, Peter.
can we open the mic? Anybody have any other comments or questions before we go? No? Is someone there besides Greg? Anybody want to unmute themselves? Okay, then I guess we're done for the day, huh? Going once, going twice? All right, guys, I'm going to stop the recording.